So I'm going to talk about a working group within LDBC called LEX, which is a kind of abbreviation for LDBC Extended GQL Schema. Just a quick word on my background. I've worked in product companies, very big ones, to startups, and lots of work in end user companies, particularly on internal frameworks and internal product projects, distributed computing, distributed transactions, database management, and ending up in the graph data space since joining Neo4j in 2016. I left in the beginning of 2020. One of my responsibilities within Neo4j was the adoption of OpenCipher and also orchestrate the initiation of the GQL database language project within ISO IEC JTC1. I also co-chaired a W3C workshop in 2019 during that time, and that was on the theme of creating bridges between RDF, property graph, and SQL, which I think is an interesting aspect of everything that we're talking about in a meeting like this. Currently, I am the part-time vice chair of LDBC, and alongside boring administrative and legal stuff, I also am one of the 3 representatives of LDBC on WG3 because of the liaison we have. Now, back in 2019, I think, put forward the GQL manifesto that led to the successful initiation of the GQL language project. And one part of what we talked about at the time when this project was initiated was the idea that there would be a GQL community, and LDBC was seen as the right place to organize that kind of community support for this work. And the intention there was that it would be possible for people to become involved who didn't have the capacity or the finance to be involved in the formal national standards bodies in the evolution of GQL and SQL PGQ. And the work that we're carrying out with respect to proposals for extensions to GQL schema is an example of that kind of community effort, and it's open to anybody who's involved in LDBC, and it would be great to see that aspect of our community work expanding. So the LEX project was set up at the end of 2022, and I think we will end up finishing in January 2024. GQL does have schema capability in the form of graph types. We've heard those described, but there are many aspects of schema which are not addressed by graph types. They're the sort of beginning of the picture, and there are a lot of constraints, for example, that can't be specified in the current version of GQL. So a year ago, we sort of started the idea of reinitiating work in LDBC on property graph schema, and this time having an orientation towards a proposal for a concrete schema language, which we would feed into a potential GQL 2.0. And last week, we actually presented the results of the first half year of the activities of this LEX group to the WG3 standards committee that's responsible for SQL and GQL. So hopefully, we will continue to feed into the formal standards process. Now, the fact that we've had that orientation towards GQL doesn't mean that the ideas around schema might not be more broadly applicable in terms of other graph data models, but that's been the sort of orientation and the axis in order to sort of ground the work and give it a sort of defined focus. One of the things we wanted to do is take in work from the old property graph schema working group, which is very active in 2020 to 2021. Its work has resulted in the PG schema paper, which Jan is going to be talking about. But there are features, particularly from SQL schema and also from conceptual data modeling techniques like EERM or UML class diagrams, plus the example of Shuffle in the RDF world, which indicate that there are plenty of things that we could actually bring into the schema picture. So the way the project's organised is, I think there are nominally about 35 working group members. It's about 15 active participants. various, obvious companies involved, which is great. We've had meetings every 2 weeks, roughly, so I think that's been about 11 working group meetings, 3 themes or subgroups, which I'll come back to in terms of the content, use cases and requirements, which Denise from AWS has been heading up. JSON schema, we've had a guy who works for Bloomberg in London, Dominic, who is known to a lot of people and has done very interesting work with his colleagues on GQL grammar parsing and so forth, and was sort of active in the concrete syntax of PG schema, looking at the area of JSON schema, and named types and labels and aliases is something that we've sort of been gathering around fairly recently. Future work items that have already been identified and had some discussion, but not really any sort of serious discussion, include things like the idea of schema graphs, schema subgraphs and how they might relate to transactions, referential integrity, subgraph constraints, and common topological patterns within data models and how they might be reflected into a schema language. The charter you can find at the link here. In fact, it's one of the documents that are sort of precursors to the work, which can all be found at the LDBC website on the publication page. If you put schema into your search, you'll see the charter at the top and a number of documents, including the summary of the work from the old property graph schema working group that led into the genesis of the GQL type design and some of the schema ideas we're looking at here. So in terms of foundations, we've got this idea of a GQL graph type. So GQL introduces a catalog, it's hierarchically organized, it can have a schema, and inside a schema there are schema objects, and one of those object types or kinds is a graph type. And a graph type has 2 sets, node types and edge types. Node types are characterized by a content type. So content type is the union of the labels and property types, which are associated or which are taken jointly and considered as a record type. An edge type also has a content type, but it has orientation. As the GQL data model supports directed and undirected data. It is directed, we need to know what the direction is. And we also need to know the node type of the endpoints of the edge. And as we can see that node types are characterized by content types, we could actually say that an edge type is characterized by its content type, and the content types of its node types or its endpoint node types. Now, a graph in GQL can be untyped and therefore schema-less, or it can have a graph type. There's nothing in between. And so if it has a graph type, it's very similar to the application of schema in SQL, and will rigidly constrain the contents of the actual graph, the data graph, the instance. And a graph is conformant to a graph type if its elements are all in a node type or an edge type within the graph type. The second piece of foundational work is PG schema, and I'll try and go over this very quickly, and Jan will be able to deal with it in more detail and handle any errors or questions. So we should probably focus discussion on PG schema to his presentation. But it adds the idea of content types defined independently of element types. They're called abstract types in PG schema. It deals with union and intersection typing, and therefore in the shape of intersection types, because they're record types, we have form of inheritance or extension. There are strict and lax graph types. There are extensible content types so that you can actually omit optional labels or additional labels, additional property types that are not specified. And there's also a concept of type names, but I'll come back to that in a different context. Is that a reasonable summary, Jan, for this purpose?
Yeah.
Cool. Okay, so some extensions we've been looking at. So we've been talking about JSON schema. So the motivation here is that it's very common for people who actually want to have nested data, document data associated with the elements of a graph, the nodes and the edges. And industrial products provide support in various ways for doing this. For example, type graph has supports a JSON type. Neo4j has extensions of the APOC library that make it very easy to push in and pull out JSON data. And more generally, you could say, well, if we have the idea which is present in GQL of nested records, the sort of conventional view of the property graph as having properties which are key value pairs up at the sort of associated with the elements. Well, if we actually allow those to be nested, then we've actually, you could almost say the property graph is a graph of trees. It is, that's what we're actually, that's the data model that we're working with. So that immediately then raises the question, can we leverage JSON schema, which is very, very, very prevalent, de facto standard, it's a community that's working towards formal standardization. If we use JSON schema, we get a lot of things for free. We get things like nested property types, type structures that are named that can be reused. Those could include usage of that facility for refinement types on the actual primitive data types. So that lets us define domains in an SQL sense. There are cross-field dependencies. We can use union types to allow us to define, non-numeric representative. I'll take the example of floats. We could have not a number or positive or negative infinity as well as numeric strings. There are all kinds of constraints in terms of ranges, string pictures using regular expressions and so forth that can be applied. And none of this has to be invented or specified all over again, just because we're working in this particular graph context. Now, Oracle 23C has some very interesting features in terms of support for JSON schema in their database product. It's a proprietary extension. It's not part of the SQL standard, but they've been able to leverage JSON schema to good effect. We actually started talking about this before we realized that Oracle were following the same sort of line of thought. So one of the key issues in doing this is to actually be able to define primitive types which come from the database standards rather than coming from the JSON schema standard, which has a very limited repertoire of primitive types. What we show here is the idea of defining a sort of miniature schema that allows you to say there is something called unsigned integer 64 in GQL. There is a database type which will tell you where you're going to find the definition of that type. So that's an external hook to an external specification. There's the JSON primitive type that's associated with that, and then we can actually put minimum and maximum bounds in order to simulate or emulate or approximate the constraints that are actually truly defined somewhere else in terms of what this type actually means. That means that you could give this kind of special type to developers, and they'll be able to use fairly standard tooling to actually, improve the quality of the instance documents they were creating and so forth. But the true validation would actually be applied by a database implementation, and that would mean that when you define the JSON document, you were able to put string representations in the leaf nodes of the document which matched the type specification that's implied by this kind of schema JSON document. This implies that there is actually a natural language specification saying what's going on around here, and that's called a dialect, a vocabulary. And so what we've got here is an identification that would say this is something that's been authored, an extension to JSON schema that's been authored by WG3, and here are the sort of characteristics that it would have. Now, that's exactly how Oracle did it, but it's the same sort of principle. If we had something like that, and that would mean that the database vendor would be able to understand exactly what the information was going to map down to when it was stored inside the database, we could also have a reverse sort of specification which said, here are the primitive types, what do they actually map to in terms of GQL or SQL types? That would probably work pretty well for the nested property sort of part of information that's associated with a graph element. I think the consensus that sort of developed both within the working group and when we talked to WG3 about this is that property graph specific features like labels or the actual mappings between content and element types, keys on element types, all of these kinds of ideas belong in the GQL native schema and native DDL. This then raises the question, if this seems like a reasonable idea, is it the way of dealing with nested data? Should we just do this and not try and write a whole chunk of the GQL specification to over-define this area? Or alternatively, should we be narrower than this? Should we say that this JSON schema capability is only going to apply to a JSON data type? So if we added a primitive data type JSON into GQL language, which is what's happened with SQL in the last iteration of SQL, we could use it more restrictively. Can this be shared across SQL and GQL? There's a theme in the history of trying to align SQL and GQL, which you can see showing up very visibly at the graph pattern matching level, but it's also been quite deliberately an attempt to make sure that at the data type level, SQL and GQL are aligned. Also in SQL, the SQL specification standardizes JSON path. So there is a variant of JSON path that's already been defined in a standard fashion, and we could use JSON path as the path language for going through hierarchical data, which would imply that, and this can already happen with SQL PGQ, that you could have a mixed path where you actually use the path language of GQL, and then you cross over into JSON path in order to actually penetrate the document structure. So that's one area that we've been looking at. Another area is what we've called type keys and aliases. So GQL is a structurally typed language. If you have the same set of labels and the same set of property types in a content type, then across the two content types, then those two types have the same semantic. So we have discussed the idea that a subset of the labels could functionally determine the whole content type. And then if we have a set of content types, which is what a graph type represents, we sort of create this collection of content types and map them to element, to node and edge types. So we have that kind of set, then we would be able to define type keys. We'd be able to say this subset of labels is a key which will identify a type. And of course, if the subset of labels only has one member, then we effectively define a type name, which is a label, which is a sort of a nominal label if you want. And then we could have syntactic sugar, which already exists in the GQL specification, for saying here's the name of the type and here's the property types, the very simple case, the sort of 80% case. But what would actually be going on underneath the covers is that name would translate into a label, and therefore the label would become part of the structural type. So effectively, we would simulate or get the effect of nominal typing without changing the type system of GQL. One of the important things about that fact of not changing the type system is we're also not changing the graph pattern matching language. So if you wanted to match by named type, you would in fact be matching by a label, and that means that the graph pattern matching language will work in a completely unaltered fashion. So there's a range of possibilities here, because this is not being suggested as something that's mandatory. We're saying you can have this determining subset of labels and use it as a proxy, including definitionally as a proxy for the whole content type. But you could also not do this at all. You were not restricted to having a single label. You could have multiple labels, which is part of the GQL data model. So the GQL data model discussed this whole issue of labels and where do they fit and what are they called, and it said we're going to allow n labels on an edge and n labels on a node. The implementation choices about what the maximum value of n might be, but we don't have this idea that there's one label on an edge and then you have multiple labels on a node, which is what you see in Cypher, or you see another variant of that in Gremlin, and so on and so forth. So none of the power of the property graph data model as defined by GQL would be reduced, but it would give us this ability to name types, talk about types by their name, use that to mean that the syntax that we were using for the definition of other things like edge types, for example, would be as compressed as possible. So the idea is to try and get schema patterns that help you understand what the shape of the data could be inside the graph that are as visual and as simple to assimilate as possible. You're not sort of cluttered with the details of what's going on with the property types and so forth. We've also discussed and proposed that aliases should be added into GQL so that you can give an alias which is, unlike a type name, does not induce a label, it does not affect the actual structural type, and that would just be convenient from a DDL perspective for all the usual reasons that it's nice to have aliases. So those are two areas we've looked at in detail. Just to very quickly sort of rattle through some possible futures, we have schema graphs. Is something that a lot of people have talked about, because if you look at the sort of this idea of a graph type is a set of node types and a set of edge types that looks exactly like a graph is a set of nodes and a set of edges, and then you think, well, why don't you make a graph? And there's a long history of using schema graphs as a way of actually thinking about conformance or validation through things like graph homomorphisms and variants that can generate that in terms of simulation or by simulation. So here I put forward, and this is not something that's a consensus within the group, this is based on work that I did with a consulting customer, that you would have a content type lattice. So here we're talking about information in a catalog about SQL metadata. What is a table? A table is something that's audited and it's a schema object. And what kinds of tables can we have? Well, we can have base tables, we can have derived tables. So those kinds of subtype relationships are implicit in the way in which record types relate to each other. We then say, well, knowing all of that, having that structure, we've got a mapping from something called a table to a node in the actual true schema graph, where one node represents a node type and an edge represents an edge type. And that is how we can actually represent the correspondence between the way in which we define these content types and the actual element types, node and edge types that exist inside the graph. If we have that schema graph with its associated information, we can run graph pattern match queries on the schema graph. Now, graph pattern match queries are usually thought of currently in the existing specifications as leading to the extraction of a binding table, so that you have a tabular representation of information that's held inside the graph. But inside that tabular representation is actually the definition of a subgraph. So this is a sort of classic pattern. You have a data graph, you have a pattern graph, pattern match defines a subgraph. If you see something like the Neo4j browser, it gives you a visual picture of the subgraph. When you do a query, the way they do that is they just deduplicate the references to nodes and edges in the returned binding table, and then it turns into a graph, a subgraph. So every GQL query defines a subgraph. We've already got the concept in PG keys and in other schema languages like SHACL of actually allowing a query to be the basis for defining constraints. So we could say, well, if we have standing queries that are part of the definition of the graph schema, they refer to the schema graph, then we can define schema subgraphs. Now, those subgraphs are useful for various things. So various things include, what about the transactional problem? Because if you look at something like PG schema, it provides a baseline of how to validate an instance, the database, against the schema. Say, is it schema conformant? But databases don't do that. Databases operate on incremental conformance checks, so that the operator of a transactional database, like an SQL, you say, I'm going to work on these tables. That narrows down the scope of what we're dealing with. And I'm going to have predicates that will narrow that down further as well. And there'll be constraints operating and so on and so forth. And so we get this minimum space that the query optimizer has to operate over, and it's also the space for static analysis in terms of the actual preparation of the query. What's the moral equivalent of that in a graph context? Because at the moment, we just go in GQL, let's do an insert or let's do a merge, and the system has to try and infer the area of the graph that's actually being operated over. Here we have the possibility of having the same kind of knowledge that we have in SQL, but the knowledge is not about tables. And actually, this relates to another more sort of functional point from the user's perspective. So in this example, you can't put a column into the graph database that represents a metadata catalog unless it is in a table, and that table is inside a catalog if we're dealing with MySQL, or it would have to be column, table, schema, catalog if it was an SQL standard observing database like Oracle, for example. So we've got the ground, sort of schema graph that says this is the kind of information that could exist, and here's an example of one of the units of insertion that's actually permitted. Okay, I will try and finish as fast as possible. Referential integrity graphs are not visible as graphs, but they're there in SQL. We have edges in our world, and so referential integrity is not only an implicit graph, it's actually an explicit subgraph. So that means that we've got another example of subgraphs and how they might be used. We have complex constraints on subgraphs. You run a query, you've got variables give you access to different parts of it. You want to make statements about those different parts of it. Let's look at PG keys. Final point is on topology patterns. So there are patterns like trees, which are commonly used, and we have users laboriously defining them, when in fact that's a waste of time. They could just say this is a tree structure, and we'll have some standard way of actually manifesting that into the underlying instance data. And I think I have remembered the second example of this, and that is, it keeps going from my mind, it's a good example. Yes, there's one gap between entity relationship modeling and what we do in this whole world and the way property graphs work and so forth, and it's n- ary relations. If we allowed n- ary relations to be defined in the schema, we could also have standard way of mapping those n-ary relations down to representation or implementation defined ways, but ways of actually mapping that down to representations in a standard property graph data model. So there's lots of work to do. New participants are very welcome. We should bear in mind that schema graphs can be queried, so they're a form of information schema which doesn't exist at the moment in GQL, and this kind of pattern-defined schema graph with these other characteristics might be very useful for other models, not just for the property graph model. So apologies for running over, Gabor. Any questions? Yes, or do you want them? Yep.
So you had that little snippet of JSON schema where you, if I understood that correctly, defined a new sort of a 64-bit integer type. And I'm curious how you see that being used. So I can see two possibilities. So is that documentation in the sense that all that is actually hardwired somewhere else in the system? Or is that sort of an operational definition that could be actually interpreted by the underlying system, so that you could really actually define completely new data types without changing the code underneath?
The answer is both. So in one sense, this is part of a specification that states how we actually, if we make a statement that something is a GQL unsigned 64-bit, then the validator, from a JSON schema perspective, could either treat that as an assertion, something that has to be enforced for real, or it could treat it as an annotation, basically documentary of what the user's intent was. The idea here is that this is actually operational. That if you made I didn't have the space or the time, but if you have a $ref to this thing, instead of saying type in your JSON schema, it will pull this bit of schema in and validate the string for that particular leaf node value against this. And this is a piece of schema that says it must be an integer, it must have this min, it must have this max. And in addition, if you're a smart validator, one that's a database type aware, you will know exactly what that means or what a date type means that comes from 8601 or whatever else it might be. So if you use a dumb validator when you just get out of the box, this will get you quite a long way. But we can't use, for example, regex expressions to define the actual characteristics of a date. It won't handle leap years, it won't handle the 29th, the 28th of the 30th of February and things like that. So the way I think of it is, this will help you approximate closely to valid data, which would be useful if you're in a development mode and you don't have to be tied to the database. But when you use it against the database, you can have a smart about data that's very precise and will say, you've just provided me something I can't force into, such and such a numeric type or whatever it might be.
Any more questions? There is one from Giacomo.
Oh, there is.
Yeah, just go. So actually, I have a good question related to the hierarchical types and its expression through the JSON path. So what is actually the representation of the hierarchical types within the graph schema then? But then it's going to be navigated and associated with the node.
So there's two sort of levels of this. One is where we want to have hierarchical information, which is part of the properties of a graph element, and that's the JSON schema part of the world, and you could imagine accessing that through JSON path. The other idea of these topology patterns is at a schema level, we haven't defined any of this. We have some kind of construct that lets us say, here's a tree, and how do we understand the boundaries of that tree? And it's just an idea. So what that would have to mean is that there was some way of having syntax that would enable us to say that this zone of the graph actually conforms to this particular topology pattern. It's still part of the graph. It can be queried in exactly the same way, but there would also have to be mappings to some kind of standard understanding of what does a tree look like. So instead of everybody reinventing parent-child relationships or has relationships or contains relationships, there would be some kind of standard understanding of that. And you can see this in some commercial products where trees are kind of close to being first-class citizens in terms of the way in which information is organized. So it's a to be thought through. Yeah.